This is the lecture for Wednesday, March 18th. Today we will be starting the topic, the nuclear many-body problem. And this lecture is originally written by Vitek Nazarevich. The nuclear many-body problem is solving the Schrödinger equation. Psi is the wave function, h is the Hamiltonian, the little hat means it's an operator, and E is the energy, so this is an eigenvalue problem, or the time-independent Schrödinger equation. The Hamiltonian has two parts to it, a kinetic energy and an interaction, or potential energy. The kinetic energy operator looks like, for non-relativistic particles, it's p squared over 2m, and we have a sum over all indices for the particles from 1 through a. And the interaction then, we have pairwise interactions, or two-body interactions between pairs of particles. So 2b refers to two-body. So we sum over all pairs I and j, I not equal to j. That gives a two-body interaction, and then we have a three-body interaction I, j, k, where I is different from j, which is different from k. And so the wave function psi now will depend on the coordinates of these nucleons, and because we're in 3 dimensions, there will be 3 times a is the number of particles, number of nucleons. There'll be 3a coordinates in this position space. The nucleons can have spins, so if I look at the z component of the spin, it can be +1/2 or -1/2, or if you want to call it up and down. And so there'll be a of them. And the nucleon isospins, meaning that they can be the protons or neutrons, or if you think of it as +1/2 or -1/2, again we have then T1 through Ta. We have a of these. And we will then try to solve for an eigenstate with one of these eigenstates with a definite angular momentum, some parity, and some isospin. Now, there will be a lot of coupled equations that we'll need to solve. Okay, so there'll be a function of 3a dimensions, but they'll be coupled together with, now we have a spins, which can be plus or minus 1/2, so you can think of it as 2 to the a power. And then we will have all of these nucleon isospins, or protons or neutrons. So if I have n neutrons and z protons, the number of ways of choosing which ones are protons and which ones are neutrons will be a factorial over n factorial divided by z factorial. Okay. Let's go on. So here are some wisdom by Steve Weinberg, who is responsible for a lot of the developments in understanding the strong interactions as well as the weak interactions. So Steve Weinberg's laws of progress in theoretical physics. This is from a book edited by Guth Wang Jaffe, called Asymptotic Realms of Physics. And the first law, these are just sort of folklore statements that people sort of have committed to memory and try to follow. The first law is the conservation of information, okay? Meaning you will get nowhere by just turning equations, right? I'm not sure that's particularly useful, but it's just a statement. Second law, and this is just another amusing statement: do not trust arguments based on the lowest order of perturbation theory. In other words, perturbation theory is a systematic expansion in terms of powers of some small variable, and don't be too lazy and just base all your decisions upon the very lowest order. Okay, but the third law is the one that gets the most attention, and the third law of progress in theoretical physics is you may use any degrees of freedom you like to describe a physical system, but if you use the wrong ones, you'll be sorry. Okay. So in other words, you have a choice as to how to describe what's going on, but if you don't make a good choice, you probably won't be able to describe it very well. And so there's a little cartoon here. So here's the doctor and the patient. The patient says, doctor, it hurts when I do this. And the doctor says, then don't do that. Okay, it's supposed to be in connection with that third law. All right, so then choosing the degrees of freedom is useful, or choosing the degrees of freedom carefully, wisely, is very useful. So how shall we select the degrees of freedom so that we can get an answer easily, or at least have a chance of getting an answer? So there are different energy scales that we want to try to describe nuclear forces. So if we start from the highest energy scale, all right. So when we're at very short distances or high momenta, high energies, you are able to see the fundamental particles, as far as we know, the fundamental particles, the up and down quarks, the gluons. Okay. If you don't probe at that very small, by the way, the technique, the main technique you can use to describe this physics is, well, you use quantum chromodynamics, but one of the techniques is lattice quantum chromodynamics, which we will discuss a bit later, perhaps next week. And if you then go down to a somewhat lower energy scale, and this is an energy scale of about 940 MeV, is when you see bound neutrons and protons. That's the approximate mass of the proton or a neutron. And so you can try to describe then what the quarks are doing inside of this proton or neutron. Well, this is a neutron, UDD. There are various models for describing what's going on, but lattice QCD is this putting quantum chromodynamics, the fundamental theory of the strong interactions, on a lattice, dividing space and time into a lattice, and then doing calculations on a supercomputer using this lattice description is in some sense the gold standard for doing these calculations. If you go to lower energies, maybe 140 MeV, that's the typical scale of the rest energy of a pion. And that pion is actually also responsible for mediating some piece of the strong interactions. And so that's where you might see a description in terms of protons, neutrons, and pions. So you don't resolve the internal structure of the proton anymore, but you just describe how protons and neutrons interact through the exchange of pions and the interactions with pions. Now, if you go to even lower energy scales, maybe about 8 MeV is the energy for the pulling out a proton from a lead nucleus. Okay, and so in that case, you might have a description in terms of just nucleonic degrees of freedom, maybe even a slightly simplified approach using, for example, some shell model calculation. And then if you go even lower energies, you might want to try to describe some low excitations, like the first vibrational state in a nucleus like tin. Then the energies would be about on the order of 1 MeV. And so then you might use something like density functional theory. By the way, the CI stands for configuration interactions, just basically writing down some shell model calculation. And ab initio just means from first principles. If you go even further down, and maybe you're trying to understand some very low rotational excitation. So remember we were talking about deformed states and having these rotational excitations you can get. So this would be on the level of about 43 kiloelectron volts, or 0.043 megaelectron volts, and that would for this you would have to use you would prefer to use some sort of a collective model to describe these rotational states. Okay, so here is the whole idea of, as you go up here, you increase the resolution. You go down here, you're removing degrees of freedom and trying to get an effective description of what's going on without getting all the complexity of all the higher resolution scale objects. Okay, so you can talk about there's an interface between the hadrons, the particles that are strongly interacting, and the nuclei. So there's the general term for this idea of using the effective degrees of freedom as you go to lower and lower energies, and it's called effective field theory. Okay, the word field theory describes the combination of quantum mechanics and relativistic mechanics, as well as the description of how many quantum many-body systems behave. The word effective is this whole notion that as you go to low energies, you can change your degrees of freedom and ignore things that are at much smaller smaller distances than what you want to resolve. Okay, here is the nuclear landscape. We've seen charts like this before. So we have neutrons in this direction, protons in this direction, and so there are the different approaches that allow you to go to rather lightish nuclei, so you're going from first principles, ab initio. If you use some shell model approach, you might be able to then go to quite a bit further, okay? But then if you use density functional theory, then you may be able to then span the whole chart. Of course, as you trade from one to the other, you lose some predictive powers, and you are becoming more and more empirical. You're getting some unknown parameters from the actual experimental data. Okay, so so I should mention the dimensionality of the problem really increases very rapidly as you increase the number of nucleons. Okay, and so here's just a statement that there's an exponential, well, there's a very rapid growth in the number of processors that you need as you increase the number of nuclei, the number of nucleons in the nucleus. Okay, let's start off with the first principles approach, so ab initio theory of light nuclei, nuclear matter. This is actually the research that I'm doing. There's various different methods. So a couple of them are quantum Monte Carlo methods, where Monte Carlo methods is where you use random numbers to sample things. So for example, if you're not familiar with Monte Carlo, suppose you want to know the area of a circle, and let's say this is obviously a square, but when I'm going to draw a circle inside of here. Suppose you want to know the area of the circle. Okay, and what you do is you first draw a square, and you know that the square has an area of 1. So the idea is you close your eye, and you just drop your pen randomly, okay, and make random points, and then you do it many, many times, and then you find how many points are inside the square, and then so you have the number of points inside the square, okay, in the denominator, and then the number of points inside the circle, and that ratio of the number inside the circle over the number inside the square gives you the ratio approximately of the area of the circle to the area of the square, and so you can then get an estimate of what the area of the circle is. Okay, that's what Monte Carlo is about, and quantum Monte Carlo is applying this to quantum system. And now the no-core shell model. So shell model we've discussed before. Shell model is SM here. A no-core shell model means you have all of the nucleons be part of the calculation. You don't freeze any degrees of freedom. You don't simplify the calculation. You do the full calculation. There's another approach called the coupled cluster method, where you basically what you do in that case is based upon, again, some shell model picture, and you have, but what you do is you think about excitations away from some closed shells, and you do calculations using some truncation of the number of excitations away from the closed shell in your calculation. We'll come back to this a bit more when we talk about the coupled cluster method. All right, so now the way these ab initio calculations work is we have some 2 nucleon and 3 nucleon interactions, and then we, by the way, you might be wondering why not more complicated interactions. Well, there's a general principle that at low energies, the 2-body interactions are dominant, the 3-body interactions are subdominant, and the 4-body interactions are even smaller, so you make some truncation after 3-body interactions. All right, so you might then do something called renormalization, which means you try to change the resolution scale again, as we were discussing before. You try to make the interactions a little bit easier to work with by doing this renormalization, or you can, in some methods, you don't have to do this at all. And then you put it through some many-body method, like we discussed, quantum Monte Carlo, no-core model, a couple of cluster methods, and other things, and you then calculate some observables for the nuclear structure or reactions. Okay, so you can get some really excellent forces. You can tune these interactions to reproduce the scattering that you see in experiments, these so-called phase shift analysis. So EFT stands for the effective field theory, which we discussed, and this SRG, this word is called the similarity renormalization group. It's not that important for you to remember that, but it's one way of trying to make the interactions a little bit easier for this step here to what's called softening the interaction, so that this method converges more quickly. And here's kind of the current status of things. So we started off with, well, the deuteron was the A=2 system, and people could do that many years ago. That was quite simple. Then in about 1980s, we could do the three-body system with about 1% accuracy. And then, so in the 80s, they could do the three-body system and the four-body system. And then people started doing larger calculations in the 90s, the five-body system, describing the neutron with an alpha. And then what you see is that up to maybe 2011, we could go up to 12 particles, carbon-12. But then what you see beyond 2011, there has been a lot of progress, and so now we've gone up to, with first principles methods, up to over 100 nucleons today. All right, so it's increased exponentially according, like Moore's law. So some of this is due to the fact that the computing power has increased exponentially. However, a lot of this is also the fact that the new methods scale much better than some of the older methods that were used. And also another facet of this is the fact that this step of renormalization that we talked about when we're talking here, of trying to make the interaction a little bit easier to use for the many-body calculations, that's also played a big role. So let me tell you about one of the methods, Green's function Monte Carlo. So this is the idea of, basically you have a Hamiltonian and you do e to the minus h tau. Okay, so the usual time evolution operator, e to the minus I h t. So I'm by the way, I'm dropping factors of h bars. Usually you would see an h bar, but we're not worrying about that. That's the usual time evolution operator. Okay, but we're going to actually do it without the I, and do it without the I. And the reason we do it without the I is, well, we're not really doing the time evolution. We're instead using this as a low energy filter. So think about the lowest energy. So let's say there's some energy spectrum for H, all right? And just think about, so we have eigenvalues, some energies like this. And what will happen, notice we will have the exponential minus this energy tau. So as tau gets large, if I have a very high eigenvalue, like 100, you'll get e to the minus 100 times tau, so it will be suppressed very, very quickly, very, very much as tau gets large. But if I have a low eigenvalue, so let's say like 0.1 or even a negative value, then it won't be suppressed relative to the high ones. Okay, it will be enhanced. So these high energy states will die, but the lowest one will be dominant. So that's the idea of this. It's just basically to do the what's called imaginary time evolution with this tau rather than this IT, to try to get a low energy filter that pulls out only the lowest energy state, eigenstate of the Hamiltonian. So that's what you do. You start off with some trial wave function, okay? And it doesn't really matter as long as it has some overlap with the actual wave function you want. And then you do e to the minus h tau. You can actually subtract the ground state energy to try to make the normalization not blow up on you, but this is not essential. And so then you can project it, if you project in time large enough tau, then you get something proportional to the ground state psi 0. So the idea is you project for some finite time, and then you try to get a good approximation to psi 0. Okay, so you start off with psi, the initial trial wave function, and then at time t equals 0 and time very large, you get the ground state. So the way you actually do this, though, you do something called the Trotter approximation. All right, and you break this exponential up into a bunch of steps, and then little time steps, and then you do enough steps so that you reach the tau you want. So there are various methods based on this approach. So you can do actually this is a list of different approaches. So we just talked about quantum Monte Carlo. This is also called Green's function Monte Carlo, and they've done calculations, for example, of carbon 12. And then there's another method that we will talk a little bit more about, the no-core shell model I discussed. That's where you do the shell model and you allow all the nucleons to be part of the game. You don't make any approximations, and they've done calculations, for example, of carbon 14, fluorine 14, as well as all the other light nuclei. And there is an approach called Fadeev-Yakubovsky, which is basically solving exactly some integral equations. And this technique is rather computationally expensive, but this has been used to solve up to the 4-body system. They're starting to go up to the 5-body system. Lattice effective field theory, this is actually the technique that I'm involved in. You do quantum Monte Carlo simulations on a lattice, and here we've done some calculations of carbon 12 and the special excitation of carbon 12 called the Hoyle state. And we talked about the coupled cluster method. So that, as I said, was basically you start from some shell model basis, you fill up to some closed shell, and then you allow for various excitations above this closed shell. So if you have some particle above some closed shell, it's what you call a particle. But if you have some particle that's below that's missing from the closed shell, that's what's called a hole. And so in this coupled cluster calculation, what you do is you stick to a certain number of particles and holes, and you make an approximation allowing interactions between a certain number of particles and holes, but you iterate it so that you can get some very strong coupling features from that calculation. And then there are other techniques like fermionic molecular dynamics, which is a variational calculation. I'm not going to go into all the details of all these things, though. Okay, here are some results from the Green's function Monte Carlo calculations. So here's just a chart of some of their successes. This is the calculation. I know it's a little small to see, but what you can see is the first out of the three is a calculation just with a 2-body interaction called argon V, V meaning potential energy, V18 meaning that there are 18 parameters. So the first one is, so this is different nuclei, different excitations of the nuclei, the spin and the parity. And the first thing is the answer you get with just the 2-body interaction. The second one is the one you get with the 3-body interaction included. Okay, a particular kind of 3-body interaction called Illinois 2. And then the third one is the experimental value. So what you can see is the first one is not that far away from the third one, but then with the second one with the 3-body interaction included, it's actually in really pretty good agreement with the experimental value. So you can see a good agreement going on here. So it's on the order of like a 1%, 2% errors up to carbon 12. And here is some calculations that I've been involved in, where there's this carbon 12, there's the ground state, but then there's also the Hoyle state, which is important. We've mentioned this before in class, but in the 1950s, Hoyle postulated that there was a about a 7.65 MeV excitation above the ground state, and that was responsible for enhancing the production of carbon inside of stars. Okay, and so here's just a calculation of the various energies, the various ground state, excited states of carbon-12, and so the Hoyle state is this 0+ state, just above the beryllium-8 plus alpha threshold. And so here's some calculations of the structure. This is just what's called the form factor, what the structure looks like as a function of momentum, and here's what it looks like in position space. Okay, and this is by the Argonne group. This is some calculations that we did on the lattice to try to understand the structure. What we saw was for the ground state of carbon-12, there was a compact sort of triangular form, whereas for the Hoyle state, this guy here, there's more of what we call a bent arm structure, an extended sort of quasi-linear but not quite linear sort of a bent arm structure for the carbon-12 Hoyle state. Let me, perhaps we can, let's see, we can stop here. This is a fun place to pick up next time. So next time we'll talk about the anthropic principle, and I'll talk to you then. Bye.